Let's start. I want to hear high energy one because you need it. We're going to see a lot of equations. These are not tough equations, these are simple. So you need that energy, okay? So good afternoon, everyone. There you go. Okay, so any question before we start our lecture? Any concern? Question? No, all good? Bless you. So, okay. Going back, let me start with our, remember last class, I wanted to talk about this last slide. We couldn't do it, or we decided not to do it. And then now we're going to go over this. In fact, this is good because this evaluation is going to be related to what we're going to learn for our class. Why clustering evaluation in general is so important to us? Because whatever we have learned so far, all the unsupervised learning algorithms, if we cannot evaluate them, so essentially it's pointless, right? There is pointless work that, okay, why this clustering algorithm will do well, why the other ones don't do well, and so on. So it is important to us to evaluate them. That's why this lecture is quite important for us. So this is just the conclusion of everything that we had previously for all these clustering algorithms to understand what is happening there. So we're going to learn, we already learned elbow method. We learned about silhouette and graph-based measure. So Davis-Baldwin is the one that we're going to go over. And I call these internal measures. Why we call it internal measures, it will be clear in our next lecture why we call it internal measure. So in general, many of the main kind of property of these clustering algorithm, they want to make sure that intercluster data points are quite close to each other, and intercluster data points are quite far from each other. That's what they measure in general. So let's look at what Davis-Baldwin is doing it for us. So what we need to calculate, I need to calculate mu for each cluster, but anyone remembers any other clustering evaluation that we had to calculate mu among all of these? It was mu in and mu out. Silhouette, right? We calculate mu in and mu out, but essentially mu was the average of the distances. But here mu is the actual definition of average of data points that we had like for many other algorithms. So how does it work? So let's say I have 3 clusters. Cluster 1, cluster 2, and cluster 3. Let me call this one 1, 2, and 3. So what I need to calculate, I need to calculate mu for each cluster. So this becomes mu1, this becomes mu2, this becomes mu3. Okay, so we have 3 of them. In this notation, sigma, we know it as what for us? Anytime I use sigma, sigma tells us about standard deviation, variance, and it has the same definition here. So we call it dispersion. How do I calculate it? By the way, this notation for us means what? This delta, lowercase delta. This is distance for us, right? This is distance. Okay, what type of distance typically we use? Euclidean. So how do I calculate sigma mu1, dispersion for the first cluster? So what we need to calculate, I need to calculate distance of mu from each data point. So this dispersion value, I want it to be a large value or small value for a good clustering?
Small.
That's why I want it to be small, because I want data points within the cluster to be close to each other. I can do the same for this one, and I can do the same for this one. So how many I calculate? 3 of them. The other one that I need to calculate is the distance from one cluster to the other one, but we do it respect to mu's here. Mu1, 2, mu2. or mu12. So I want this, the green one, from one mu to the other one. I want it to be a large value or small value here? Large, because the clusters should be as far as possible from each other. Okay, so once I calculated all of those, then we need to calculate Davis-Bouldin index for each cluster. So here I have 3 clusters. This means that cluster D1, D2, and D3. Okay, so how do I calculate D1? I'm going to follow this equation. D1 essentially becomes maximum value of 1 not equal to J, which is dB, considering for 1, which is 1, 2, and dB, 1, 3. We're not doing it 2, 3 because we are focusing on cluster 1. So how do I calculate dB12? dB12 means what? Sigma mu 1 plus sigma mu j, which is 2. The distance from mu1 to mu, essentially this is our. So do I want this one to be a large value for clustering or a small value? For good clustering. Denominator should be a large value or small value? Large. How about this one? This one is small. So for a good clustering, this one should be small value. Okay. Why do I calculate then the maximum value? Why I consider the maximum among all of those? If I'm looking for a small value here, why I calculate the maximum one? Any, yes?
You want to find the worst case?
Worst case scenario, right? So we're looking at worst case scenario. So if I have it, so I'm going to calculate it for D1, I'll do it for D2, I'll do it for D3, and take the average. A lower value means that the clustering is better. Any question here? Any question? No question? Good. Okay. So let's go here. Clustering evaluation. So clustering evaluation is important to us, but let's have the meme of the day. Yes?
For the previous slide,
Davis-Bouldin, yeah.
why do we average it and instead of taking the max? Like we chose the maximum for worst case, why did not choose the worst case again?
So that's typically what, so many of these clustering evaluations, at the end, they take your average. Well, you're right. So we can go with the worst case scenario too. That's right. Okay. But that can be also problematic because we are considering we are focusing on one cluster at that time. We want to just look at all the clusters at the same time, right? So, but when I just calculate the max value over the maximum, because I'm focusing on one, I'm allowed to go with the worst case scenario. But when I do it for the whole thing, so I don't want to just pay attention and focus on one cluster. I want to pay attention to all of them. Yeah. Okay. So the meme of the day is going to be also related to unsupervised learning clustering. I want to see that how expert are you in finding similarities and dissimilarities. 2009 studying, 2019 after 10 years studying. So tell me similarities and dissimilarities here. Anyone? It can be, yes.
Similarities studying.
Similarities studying. Okay, fine. What else? What do we have? Yes. Wearing the same shirt? Do you know the reason? When you start as a PhD, what happens to you? You don't have money to buy new shirts. What are we talking about? So that's a part of our life, right? When you become a PhD student. I'm motivating you to do PhD, that's the reason. Okay, what else?
He has a mustache.
Mustache. I mean, with 10 years, what do you expect? Yeah, that's right. That's one thing. What else? Yes. Well, receding, hair receding, I don't know why it didn't happen to me. Maybe it happened internally, but that always happens. Okay. But look at it in a kind of spiritual way. 2009, he's what? He's smiling and he's happy. 2019, still happy after 10 years. This is magic. Right? This doesn't usually happen when you... Anyone wants to do PhD here? Raise your hand. I'm not changing your mind. No? Never. Doesn't matter. He wants to do PhD. That's okay. Okay. We can talk. We're going to talk about PhD a little bit more. In fact, I mean, I mentioned I enjoy doing PhD, but okay. Let's do clustering evaluation. I'm going to talk about external and internal. So in fact, we went over internal already. External means what? External means that we have some external information, like some ground truth information. That's why we call it external. So it implies that there are some external information so we can use those. Internal means that we don't have any external information, so we got to come up with some metrics with whatever we have. Right? Same as silhouette. There is no external information. So what do I mean by external information? This means that some ground truth information, external ground truth. Okay, so matching base, entropy base, and pairwise, we're going to talk about those. So you can see that there are a lot of writings here, text here, but the most important part is these two lines. These two lines are quite important. Okay. Please memorize this right now. Let's memorize it because I'm going to use it a lot in our future lectures, a bunch of small notation here. So K is the number of ground truth partitions. For the ground truth, I call it partitions because I reserve the word of clustering for the number of clusters. Let's say when we apply GMM, we're going to have 3 clusters. So I'm going to reserve it for our algorithm. For ground truth, I'm going to use partition. And K refers to the ground truth. And R refers to the number of clusters, and I use C for this one, by an algorithm. Let's say K means GMM or any algorithm. Okay. So K refers to ground truth, and R refers to number of clusters. So when I run my GMM algorithm, what do I need to know in advance? Number of clusters. So do I have, when I want to apply this type of external measure, do I have the number of clusters in advance?
Yes.
Which one?
Because you need another cluster.
Yeah, but here in this case, do I know it? So I don't need to optimize it. We have ground truths, what? No. We know the number of partitions already. Ground truth partitions, the number is already given to us. So this means that I already know that what numbers I should start my algorithm. Okay, numbers I need to start my algorithm. Does it make sense or not? The question becomes, if I already know it, why I should even do this? Right? Any suggestion why we need to do this? Yes.
Is it possible that you assume a ground truth, but then you evaluate it with the current cluster?
No, the ground truth is given to us. Someone has already given us the ground truth information, so we have it. If we know ground truth, why do we even need to do clustering? Yes. Yes, definitely we can do it. But the question is that if I have already ground truth, why do I even need to do clustering? Right? Any other? Yes?
If you, there's a difference between knowing how many partitions there are and knowing which data points correspond to each partition. So
But in unsupervised, do I really care which partition? I don't really care, because in unsupervised, we don't care about labels. As long as our clustering will capture what I want, I don't really care about which label, which partition. Right? That's a very good point, by the way. Yes?
Should we put like a subset of the data
There you go. So if I have ground truth for subset of Y, because finding ground truth is quite expensive and difficult. So typically what we have it for subset of data, and so we do it for the subset of data. Hopefully it will translate it to the whole set of data points. Okay, very good point. So n sub ij, I refers to cluster, and j refers to partition. So please memorize these. So k refers to partition, r refers to cluster. I refers to what? Cluster, and j refers to partition. Okay. So why we need this one? Because we want to calculate this matching base measure. So I refers to what? Clusters or partition? Clusters, which means, let's say we did k-means clustering. Okay, so it's not partition. So we want to calculate something called purity, but let's see. What do I mean by that? So if you look at here, the field colors are the ground truth information, the field colors. And this one, this elliptical shape geometry is for what? R clustering, okay? So what do you think, what type of clustering algorithm I've used here to capture these points? We use Gaussian mixture model. Why do you think I use GMM? Because the elliptical clusters. So which part of GMM will help us with this kind of elliptical shape then? Not variance. Covariance. Okay, so which part of this covariance will help me with the scaling? Which part is helping me with the rotation? Off diagonal is helping me with what? Off diagonal helps us with rotational part. Diagonal helps with scaling, right? Scaling. Quite important to understand these. Good? Okay. So let's calculate it for cluster one, because we have 3 clusters. We need to calculate 3 of them, and then we calculate the average or expected value at the end. Okay. So in order to calculate it for cluster 3, I need to know the number of data points in cluster 3. Which one is cluster 3? Black, orange, or the red one? Black, elliptical shape that I have here. How many data points I have here inside this one? 9, okay. So N31 means Nij. I refers to what? I refers to cluster or partition? I refers to cluster. J refers to partition. And that's why I put I here, purity I, because it refers to cluster. Okay, I want to calculate the purity of cluster. I don't really care about ground truth. Okay, so what does it mean that N31, the number of data points belonging to what? 3 means what? The number of data points belonging to cluster 3, and they also belong to partition 1, right? So which one is cluster 3? The black one. So how many data points that I have belonging to cluster 3, and also they belong to partition? Which one is partition 1? The field orange color. How many I have? 2 of them, so it becomes 2. How about this one?
0.
How many data points I have that they belong to cluster 3, and partition 2, which is blue, 0. Next one, 7, which becomes 7 over 9. Okay, I'm going to do a slide change here and tell me. Okay, now what's going to be the result? The number of data points which are in cluster 3 and partition 1. Which one is partition 1? Orange. Okay, so what is the number? 7. How about N32? How many blue I have there? 0. How many black I have in this cluster? 2. The result, did it change?
No.
No, it didn't change because we don't really care about what label or partition they are. As long as it can capture the majority that I want, that's what I care. Okay? Unsupervised, do we have labels? Do we care about labels? No, we don't really care about labels. I just want that cluster to capture the most out of any partitions out there. Okay? So this becomes 7/9. Are we good? So what should be the, are we good or no? Good? Okay. So what should be perfect value for purity for clustering? 1, right? So that's, I have 3 clusters here, so I need to calculate for 3 of them. So then I do this expected or average value. Expected value, Ni over N, total number of data points in this cluster divided on by total number of data points. Any question about this part? Yes.
So, in the edge case where you only have one ground truth, wouldn't the purity be 1 for every single cluster?
Then why do you want to do clustering?
So, in essence, purity can't tell us if we have the right.
Yes, so you need to have at least 2 clusters. Otherwise, one, then there is no need to do clustering, right?
Clustering. Purity can't tell you that you don't.
Yep. Okay, so what is this one? What is purity value for perfect clustering? 1. Okay, so I want you to also understand this Nij table. We call this one Nij table. What it means. The columns represents the ground truth information. The number of data points in partition, this is ground truth, partition. And these are our predicted one. Well, we call it predicted. In fact, we don't do any prediction in clustering, but typically people call it predicted, like how many data points I have in cluster 1. So how many data points I have in cluster in partition 1? This one is the summation, by the way. 25 data points in partition. How many in partition 2? 40 and 35. Okay. How many data points I have in cluster 1? 50. So we use n's. Should I use I or j here? Because I refers to clusters. Here we use m. Should I use j or I? Because j refers to partition. So I'm going to use mj. M is total number of data points. So once you have this Nij table, will make things easier for you to calculate. So if I want to calculate purity here for cluster 1, I'll look at this row and I calculate the maximum value. Which one is maximum? What is maximum value here? 30. 30 divided on by 50. 20 divided on by 25. 25 by divided. And then we take the average. Good? Nij table. What is the problem with this approach, purity calculation? So let's look at this Nij table. This one, what is the maximum value? Refers to what? Which partition? Partition 2 for cluster 1. How about cluster 2? Refers to the same partition. That can be problematic for us because the maximum value for each row, for each cluster refers to the same partition. It should tackle different partitions. That creates a problem, and that's why we use something called maximum weight matching. So what it means by this? So for this, there are multiple algorithms to look into. Just want to tell you like how we're going to deal with it and how we're going to calculate it. So first thing first, what is the maximum value for C1? Refers to which partition? Partition 2. So 30 partition 2, this means that I'm going to block partition 2. This means that it won't allow the other clusters to refer to this partition. So what is the maximum value for C2 right now? T3, 5. Then I block this one. How about C3? Just one left becomes 25. And then I start from the second one. What is the maximum value? I start now from here. So I need to block this one. So let's go back to C1. What is the maximum in C1? 20, which is T3. And then go back here. So, and then we need to just like consider many scenarios here. This means that we're going to get many purity values. Okay, the algorithm wise, again, so you got to come up with an efficient way to do it. And then at the end, you need to calculate the maximum one. Okay, the maximum purity. That's called maximum weight matching. Any question on this? Yes.
Could you maybe calculate all the purities as regular and then figure out like highest to lowest purity?
You calculate it, and anytime you calculate, you got to block that column. So the others can refer to the same partition. That was the whole idea.
What if after you block that column, you figure out that something is even more paired?
That's really your algorithm. You got to come up with an algorithm that considers all the scenarios. Yeah. So I got to make sure that I have all scenarios. So then I calculate it's a maximization problem. Yes.
So why are we choosing the max? We're kind of assuming a best case here for purity.
So for clustering evaluation here, we use max. That's a good question. So use maximum here. You're right. I don't know there might be some reasoning over there, but I can't digest it. You're right. We need to go with the worst case scenario. Yes.
Could you explain the second one, the 20 plus 20 plus 25? Why would you choose 20 for C1?
So what we are doing, because there was a swap here, these two refer to the same partition. That's why I started from the first one, and I just blocked that column, and the second one, so on. But typically, I don't know in practice which one is going to refer to the same partition, right? So I need to just start from, let's say, first one, calculate, block it, and do the rest. Start from second one, so I need to do a lot of scenarios here. And that's why the algorithm becomes quite important, what efficient algorithm we can use.
That's getting the average of all of the clusters and saying like the purity value of each one, whichever one's maximum, that's the best choice.
That's the best choice, the maximum. Not the average, yes, for each purity we calculate it based on, you're right, based on the average expected value, and at the end we calculate the maximum value. Yes.
So you need to do every permutation of the cluster.
Yeah, there are many permutations, but if some of them are not referring to the same cluster, maybe we can avoid in our calculation to just reduce the number of scenarios. So drawback of purity, we know it because it might match the same partition, so that's why we use maximum weight matching. Okay, now I'm going to explain quite important concept here called precision, recall, and accuracy. So I'm going to explain it through unsupervised learning, but typically we use this one mainly for supervised learning, but it works for both of them. So I want you to just, when I explain it here, don't just consider it for unsupervised. It can be also used, in fact, mainly it's being used for supervised. Okay, let's say I'm going to throw a bunch of darts, and this is how I do it. This is how I do it. Do you think I'm precise here or accurate?
Precise.
I have a high precision. So when we talk about precision, precision is the local information. I don't look at the global information, how complete, like I'm looking at everything. So locally, I'm doing very well, okay? Well, precision is a good thing. I'm not saying it's a bad thing, but we got to be careful. We got to look beyond what we see. Okay. How about this one? On average, do you think I am precise or accurate?
Accurate.
Accurate. So this bullseye, this is our target. And I'm average, but I may not be precise. Okay. How about this scenario? Precise, and this is something that we want, right? This is our dream algorithm. So we get both precision and accuracy. How about this awesome scenario?
Neither.
We're neither, right? So, and this reminds you of someone, and that person is myself. I'll show you picture here. I had 3 darts. I had one, like, I wanted to have, like, I had 5 chances, and this was my first one. So the first one is here. Second, where's the third one?
The floor.
There you go, here. And the guy over there is like, I'm not going to give you any, like, other choice. Like, you leave. is so bad. So let's left. So I'm none of them, but we should not be. Hopefully in ML, I'm not like this. ML is better than, okay. So let's go back to precision and recall and look at it from this table, which is a very important matrix for us. If I have more than 2 labels, we call it, there is a name for it. You got to remember this one. We call it confusion matrix if I have more than 2 labels. Here I have 2 labels, positive and negative. Consider it as this. Positive is cat, negative dog, 2 labels. Okay? If I have 3 labels, it becomes cat, dog, and fish, different scenario, we call it confusion matrix. Okay, here in unsupervised, or here in clustering evaluation, for us it's positive and negative. I just want to make sure whether it's captured by a cluster is being captured, or a cluster is capturing a specific partition or not. I don't care which partition that is, right? I just want to make sure that we capture the most out of each partition. Okay, so the row are the prediction. These are the prediction. How about the columns? Columns are the ground truth, or we call it actual, or actual. So this one means that the number of data points that I predicted as what label? This one is our positive, and this one is our negative. This means that the number of data points that I predicted as positive. Number of data points that I predicted as negative. How about the first column? The number of data points that are actually positive, the number of data points that are actually negative. The ground truth which is given to us. Okay. What it means by precision. Precision captures local or global information. Local. It says that among all the positive prediction that I've had, I'm just looking at my prediction. I don't care about anything extra. Among all the positive prediction, what portion I predicted correctly. By the way, precision can be for any label. I'm doing it here for positive. So among all my positive prediction, what portion I calculated correctly, which is true positive divided down by total number of prediction. We're just looking at things locally, just whatever I predicted. I don't look at a bigger perspective here. Yes?
Calculate this for a specific cluster?
We just calculated based on one cluster. We look at just one cluster here. So this means that we don't look at other clusters, just one cluster, how we are doing it within one cluster. Okay. Recall means, so among all the actual positive, how many of them I predicted correctly? So this is called a global information completeness, which means that we look at different clusters, not just our cluster. I'll give you an example here so you have a better idea what is happening here. Accuracy is true positive, true negative, the diagonal part, divided on by total number. What portion I predicted correctly for all of them. Okay. So let's look at it here. Don't look at this part for now. If you look at this cluster, the orange one, do you think this cluster is doing a good job or not? Don't look at any other cluster, capturing partitions.
Yes.
So locally, if I just look at this cluster, do you think I'm very precise or not very precise? Very precise. In fact, precision and purity are the same thing for us. So you can see that locally I'm doing very well, quite precise. And then let's look at a more global kind of structure here. So how many filled orange color I have? 10 of them, right? You can see that they are distributed across different clusters. And recall says that this cluster, out of all of them, what portion it could calculate? Correctly, which is 6 over? It looks at all the cluster, not just itself. More global information. Any question here? It looks at all the cluster, right? Well, precision just looks at just one cluster. Any question here? Yes.
How would you, like running with this example we have going now, how would you do like accuracy?
How do I do accuracy? So accuracy here has different definition. Maybe I can explain it into our pairwise. So we don't really care about the label here as much because I don't care whether it's partition 1, partition 2, or partition 3. As long as so possibly accuracy becomes the summation of, let me show it in pairwise. I'll talk about pairwise a little bit. So that will make more sense over there. Okay, yeah.
For recall, like, is our goal to basically have roughly the same recall values across all?
So that's a good question. What is the difference between recall and precision? Let's look at it from one example. Let's say we're going to do a surveillance camera, right? So based on the problem that we have, do you want in this problem to be more precise or have a higher recall value? So this means that if you make a mistake, that's just going to cost us a lot. So then you want to have a model with high precision or high recall? If you make a mistake, it's just going to cost you a lot. So within the cluster, I'm going to do a perfect job. So this means that I'm looking for high precision or high recall. High precision, right? This means that what I care, even if my general accuracy is not that high, in whatever I predict, I want to predict it correctly. Does it make sense? So let's say, I just gave that example, like Tesla says that my car has 98% accuracy. And then means like 2% means what? Hit and kill, right? So we got to be careful. So are we looking at precision, recall over there? This is quite important for us. And that falls under ethics in machine learning as well. That's quite an important subject when we consider all of these. Okay. So now that let's calculate precision. Precision means what? Look at just one cluster or all clusters? One cluster. Within this cluster, maximum value is 30 divided by 50. 20 divided by 25 and so on. So what it means by recall? Recall says that out of all these clusters, let's say I have how many ground truths I have for partition 3? 35. Among all these 35, okay, which cluster, I'm looking at all clusters here, again, global information. Which one has given us the best result? Like we capture majority of those. Cluster 1. So it becomes 30 over 35. Then here they have the same value. Maybe you can use some sort of matching base here. And this becomes 25 over 25. Good? So now I can calculate recall. And so in practice, what people do, they say that, okay, so I have a lot of values, one precision and one recall. Can I come up with one measurement, a metric, which refers to both recall and precision at the same time? So if that metric is high, this means that both precision and recall are high. That's the question. And what people do, they have created something called F measure, the harmonic mean of precision and recall. This means that if F measure is high, both precision and recall are high. So with one value, I can capture both of them at the same time. So we call it F measure. Any question here? Yes.
But you kind of lose some of the, you're kind of reducing it to a single dimension with that.
Yes.
You kind of lose some information.
You might. That's correct. But sometimes if I want to make sure that my model at the same time, like capturing both of them, so that's just easier for us to track.
Is it easier for optimization?
Or is it, maybe we can use it for optimization part too. And many papers also use F measure. Like if F measure is high, back of your mind, you understand that both recall and precision are high. Okay. Any question? So that's our matching base. The other one, the new one, so we're going to go to the second one, which is called entropy-based measure. Okay. So for entropy-based, what I need to do, help me here. What is this? P of x multiplied by g of x. Expected value of g of x. What happens if I'm going to change g of x with I of x. Anyone remembers what I of x was? Surprise information we had. What was the equation? Had a direct or reverse relationship with probability. Which one? So what was the equation? Log of, I said something's quite important for the base, should be base 2, 1 over p of x. The other way I can write it with the negative version, which becomes p of x. Okay, and this, what notation I use? H of x. So remember, this was our entropy, just to make sure that we remember this one. Okay, so knowing this, we can calculate the entropy for cluster, we can calculate entropy for partition. So how many clusters I have based on this example? 3, so which means that I need to calculate probability for cluster 1, probability for cluster 2, and probability for cluster 3. The same here, probability for partition 1, and so on. So how do I calculate probability for cluster 1? Anyone wants to help me? How many data points I have in cluster 1? 50. How many, what is the total number of data points? So which means that probability of cluster 1 is 0.5. 50 over 100. So this one is our NI. Probability of cluster 2 is 25 over 100. What is the probability of partition 1? 25 over? Probability of partition 2? 40 over 100, and so on. So we call this one MJ, so we have MJ. So if I have those, I can calculate entropy of clusters and partition. There is a reason we're doing this, by the way. We're going to see it. Okay, so all the lectures we had, first 2 or 3 weeks, coming here, conditional entropy. So I refers to clusters or partition?
Clusters.
How many clusters I have? 3. This means that I'm going to have 3 conditional entropy. Okay. In order to calculate conditional entropy for this, let's say T given C sub I, what I need to calculate, I need to calculate probability of T given what? Right, I need to calculate this probability so I can put it here. Right, what is the equation? Probability multiplied by log of 1 over that probability. So how do I calculate this probability? What rule I should use in probability? This conditional probability. What should be the denominator part? The general form for numerator? Joint probability of T, Ci. So, what is probability of Ci? Ni over N. What is the probability of T comma joint Ci? Going back here. This one is what? This one is Ni. Number of data points what? Which are in, and this becomes N1, 2. Number of data points which belong to class C1 and belonging to T2. So this is AND. This is AND. So the AND probability. So what's going to be the probability then? It becomes for probability of Nij, I and J becomes what? Nij over N. 20 divided by 100. Probability of C1 and T2 divided by 100. So this becomes Nij over So the whole thing becomes what? Can you cancel out these two? This becomes Nij over. So that's why you see Nij over Ni here. Okay, so I calculated for cluster 1, I calculated for cluster 2, calculated for cluster 3. Then the question becomes, how can I calculate it for the general conditional probability, T given C? Remember in our the information class, information theory, I mentioned that anytime we calculate conditional entropy, we got to calculate I have 3 of them, so how can I collapse them to calculate 1? We always calculate average conditional entropy, so the expected value, which is Ni over N, right? So if I do it here, Ni over N for the first cluster, Ni over N for the second cluster and third cluster, and that's how we calculate it. So what's the point of calculating this entropy? Why do we want to calculate it? Going back here. I'm going to put dummy numbers here. If I have 30, 30, 30 here, this becomes 90, right? So do you think, am I quite certain about the result or uncertain? What is entropy here for this cluster? Entropy is high or low?
High.
Entropy is high because
So it'd be in any of
like they have the same probability, right? We are quite uncertain about the outcome. They have similar probability, quite uncertain. So is it something that we want for clustering? High entropy. No, this is not something we want, high entropy, because then we're confused which one is which. Okay, so how about this scenario? How about this scenario? 85, 5, 5, 80. Entropy is high or low? Low. So is it something that we want? Yes. And so entropy-based type of measuring will capture like what is the entropy each cluster among different partitions and calculates that for you. Yes.
So this is, but if you happen to have 3 clusters that were really good clusters, well, I guess in this case partitions, we're talking about partitions. If we had 3 partitions that really do accurately cluster the data, but they're all around the same size, that would not be good for this, right? We want them to be different sizes.
So we're talking about partitions. That's fine, like partitions, they can capture different things here. Okay, so here. They can capture different parts. But again, I want my clustering algorithm to capture the same thing. If it does not, and again, the color doesn't matter for us. The color, which one is capturing. If it's capturing the same thing, quite similar thing, this means that I have a, let's say if I put all the black ones here, this means that I have almost, my entropy is going to be what? 0, if it captures the whole thing here.
Oh, okay. You see how it's related to the clusters too.
Yeah. Okay. Any question? So for this entropy, do I want it to be a high value or low value? For good clustering? A low value. So we are interested in fact, the minimum value is 0, and the maximum value when C and T are independent of each other. So one is completely off against the other one. They're just behaving completely different. That becomes our maximum value. Okay. By the way, the other way that you can calculate this through this equation, I'm not going to go into details because I have written the whole thing here. It's just a matter of replacing one versus the other one. You can calculate it simply here. Okay, you go to the next one. Next one, again, everyone, I know that's a lot of equations here. They're not hard equations, but they can get boring because there are many of them. I want to make sure that we understand this. This is important for us because it comes to our clustering evaluation, and it's very required for us to know it. The other one is called mutual information. Mutual information, it says that how much these partitions and clusters share information. Do you think it would be a desirable one if they share a lot of information, if they don't share that much information? No, the other way. If they share information with each other a lot, that's a good thing. This means that one knows about the other one.
Clusters share information, wouldn't that mean there are overlapping parts?
So we're talking about partition and clusters. When they share information, which means that our cluster and partition understand each other, right? So when they share a lot of information, this is a good thing for us, okay? So for mutual information, do I like a high value or low value? High value. There is a problem with this approach. We don't have any upper bound. This means that, what should we do? We need to bound it. How can I bound it? Normalize it. So we need to normalize it. So I have an upper bound, so I can say which one is bad, which one is good. The way I normalize it, I have my mutual information divided down by square root of entropy of cluster, multiply entropy of, and now the maximum value becomes 1, which indicates a good cluster. Any question here? Okay, so this is the last one. Okay, just tolerate, please. The last one. This is the interesting one too. So that's the last one. Okay. So what we need to do, we need to calculate the number of edges here. How many edges I have for 3 data points, 3 nodes? How many edges we have? 3. How do I calculate number of edges? What equation we use to calculate number of edges? N choose 2, and what was the equation? N multiply n minus 1 divided down by 2. So if I have 3 data points, becomes
3.
What happened here?
Should be over 2.
Create a new.
Here.
There you go. So 3. Okay. So what I need to do, I need to find the number of pairs here, let's say for true positive. What does it mean by true positive? It means same partition, same cluster. What is the cluster of this data point? What's the name of cluster of this data point? This one is elliptical shape C3. Okay, what is the cluster of this data point? Are we good? This one is also C3. Okay. What is the partition of this data point? Which partition it belongs to? T1. What is the partition of this data point? T1. Do they have the same partition and same cluster?
Oh, well,
Same cluster and same partition. Yes?
Yes.
So they have same partition and same cluster. How about this too? They have same partition and same cluster. Are we clear here? Okay. So let me look at this one. 20 represents what? Anyone can help me with this. 20 represents what? Who wants to help me? 20 represents, yes.
Number of data points that are in the first cluster and
The number of data points which are in cluster 1,
partition.
do they have the same clusters and same partition?
Yes, by definition.
Right, by definition, they have same cluster, which is cluster what? 1. They have same partition, which is partition 2. I have 20 data points over there. How can I find the number of edges between these 20 data points?
20
What is the equation I can use? 20 choose 2. So if I ask you to find me all the true positive pairs, the edges, how can you calculate it? All the edges, true positive one. Let's start from the first one. This one becomes what? 0 choose 2 plus what? 20 choose 2 plus 30 choose 2 plus 0 choose 2 plus 20 choose 2 plus 20 plus choose 2 plus plus.
Oh, those are some.
That's it. You keep going and I keep going with you. Like, what is happening here? 1, 2, 3. So we're done, right? Thank you for just helping me to create a. There you go. Okay, so this one becomes true, the number of true positive edges, right? The number of. Are we clear here? Total number of the pairs. Okay. Now, calculate false negative. False negative means same partition, different cluster. Okay. What is the partition of this point? The ground truth. What is the partition of this?
T1.
T?
T1.
T1, because it's filled orange color. How about this one? What is the partition of this? T1. What is the cluster of this point?
T2.
C2? Yes. How about cluster of this one? This one is C1. Do they have same partition and different clusters? They have same partition and different cluster. Okay. So help me here. I'm going to sum up these two, true positive plus false negative. What it means by summing up this column, true positive plus false negative.
All your truths.
All the true,
Actually true.
the actual positive one. All the actual positive. That column means all the actual positive. The rows means what? The first row means what? Predicted, positive. Positive and negative, like cat and dog. So the first column means all the actual cats, for instance. Okay, so all the actual ones. What is the number of actual one in partition 1? How many data points I have in partition 1? How many I have in partition 2? 40. How many I have in partition 3? Can I say that the total number of actual one is 25 choose 2 plus 40 choose 2 plus, can I say this? These are all actual ones, right? These are all actual ones. This means that these are total pairs. This means that it's equal to our true positive plus false negative. Yes or no? Anyone? Any question here? Good? Okay. So do I have true positive?
Yes.
Where do we have true positive? From previous slide. We have true positive, so we can calculate false negative. Okay, so I have another question here. How can I calculate false positive? Different partition, same cluster. Yes.
We take what we just calculated, which was our true positive plus false positive.
True positive, so the number of what? The number of? This means the number of what? Prediction or actual? Rows are prediction. How many of them are predicted as positive? Prediction. So this means what? This means true positive plus false positive. So for C1, how many of them are predicted to be in C1? 50 of them, right? How many of them are predicted to be in C2? 25. And for C3? So can I say this one is equal 50 choose 20 plus? These are all the total number of prediction. 25 choose 2 plus. Good? So do I have true positive? So can we calculate false positive? Yes. Okay. Any ideas how to calculate true negative? Different partition and different cluster. I'm going to put it yes.
I'm guessing if you have all three other values, you just find 100, choose 2, and subtract those.
Good job. So n is what? N true positive, false positive plus false negative plus true negative. Do I have this? Do we have this one? Do we have this one? So this one we need to calculate. How can I calculate total number of pairs?
Total number of data points, choose 2.
Which is 100, choose 2. All right, so we can calculate it. Okay, so why we do this? I mean, we understand the calculation, but why we do this one? Do you think having a lot of true positive is a good thing or bad thing? Having a lot of true positive. So I want a lot of true positive within the same cluster and partition. But let me put it this way. If I have this one as 10, 10, and 10, what is the number of true positive in cluster 1? Number of true positive in cluster 1. 10 choose 2 plus 10 choose 2 plus 10 choose 2. Let's say I have this scenario. What is the number of true positive in cluster 1? 30 choose 2. Which one do you think is going to give me a higher value between 1 and 2? 30 choose 2. You can see that it will give me a larger value. So that's what we're interested in. Okay, so now that I calculated all of these, by the way, this is just a slide that we already did the calculation, so that's how you can do it. Now we can calculate many of these measures. The first one is called Jacquard, which is true positive divided down true positive plus false negative plus false positive, false negative plus false positive. For perfect clustering is, oh, do not leave, we're going to do attendance. Give me 2 minutes. Okay, I hate that you missed it. I hate that you missed it. Give me 2 minutes. So we're going to do, this one becomes perfect clustering. For RAND, it's quite similar to accuracy, true positive, true negative divided down by n. This one, precision, true positive divided down by this. Recall, we can calculate it. And having precision and recall, I can calculate something called Folk's mallows, which is quite similar to F measure. Okay, so we can calculate it. Okay, so the rest of them internal measures, do we know this? Graph-based, Davis-Baldwin, and silhouette.
Yes.
Imagine I used to teach the whole thing in one lecture. No, yes, no. So that happened, and that's why I divided it into different lectures. So we already went through those. So beta CV, cohesion, separation. Here we use mu out, mu in, and Davis-Baldwin, we went through that one today. Okay, so that's for today's everyone. I'm going to, let me save this. Let's have our point solution. So what happened?